Hello, my name is DbHtS and today I am going to present our paper Tight Multi-User Security Bound of DbHtS. It is a joint work with Nilanjan, Mridul and Suprita. So, DbHtS or double block hash then sum is a design paradigm of constructing a beyond birth bound secure variable output length PRF, which was proposed by Datta et al. In FSC 20. So, double block hash then sum is based on two components, namely it is built upon a double block hash function which takes a message n and it produces 2n bits output, and then the output is fed into a sum function. So the sum function is nothing but the sum of two independent block cipher outputs, and authors have shown that double block hash then sum is a BBB secure PRF. That means it can give security up to 2 power 2n by 3 many queries. Many of the constructions which are beyond birth bound secure PRF actually falls under the realm of double block hash then sum paradigm. So in CTRSA 2010, Yasuda have proposed the sum ECBC construction, which is the sum of two independent CBC mode. So it is a red half sequential mode of operation which requires 4 independent block cipher keys, and that offered q cube l cube by 2 power 2n of the security bound. So as you can see that this mode is basically built upon a hash function, and the hash function is nothing but the concatenation of two independent CBC function followed by the sum function. Similarly, in Crypto 2011, Yasuda has also proposed another construction which is proven to be beyond birth bound secure PRF known as PMAC plus. So unlike sum ECBC, which is a red half construction, PMAC plus is a red 1 and parallel mode of operation, and that also requires 3 independent block cipher keys and offered q cube l cube by 2 power n 2 power 2n security bound. So again, as you can see that this PMAC plus is basically a combination of two modules, namely the double block hash function, which is denoted in this dotted region, and followed by a sum function. In AsiaCrypt 2012, Chang et al. Have proposed 3KF9, which is again a beyond birth bound secure PRF, and it is a red 1, but unlike PMAC plus, this is a sequential mode of operation. Like PMAC plus, it requires 3 independent block cipher keys and offered the similar bound q cube l cube by 2 power 2n. And finally, in 2017, in AsiaCrypt, Naito has proposed a construction which is called the LightMac plus construction. So this is a red 1 parallel mode of operation, and again like PMAC plus or 3KF9, it requires 3 independent block cipher keys, and it provides a better security bound, namely it provides q cube by 2 power 2n security bound. So again, as you can see that this LightMac plus is constructed out of two components. One is the double block hash function, which is again denoted in this dotted region, and followed by a sum function. And most importantly, that unlike all the other 3 BBB secure PRF, LightMac plus is the first beyond birth bound secure PRF whose security bound does not depend on the length of the message. So as you can see that all these 4 constructions, namely sum ECBC, PMAC plus, 3KF9 and LightMac plus, the underlying double block hash function takes one key. Namely, if you see that sum ECBC function, then the underlying double block hash function takes basically a pair of keys, namely K1, K3, and the sum function takes 2 keys, K2 and K4. Similarly, if you take the PMAC plus construction, then the double block hash function takes a single block cipher key, namely K1, but the sum function takes a pair of independent keys, namely K2 and K3, and similarly for 3KF9 and LightMac plus. So all these constructions are basically the instantiation of 3-keyed DbHtS paradigm. So the 3-keyed basically denotes the hash function takes a key, and the sum function takes a pair of independent keys. So altogether the number of keys is basically 3. So that's why it is called a 3-keyed DbHtS construction. So as a variant of 3-keyed DbHtS construction, Datta et al. Have proposed a 2-keyed DbHtS constructions where the sum function is basically made of a single block cipher key, namely the k, and that is independent over the hash key. So here the sum function requires a single block cipher key, and it provides a similar level of security as the 3-key DbHtS construction. And Datta et al. Actually have instantiated this 2-key DbHtS construction with the 2-key variants of some ECBC PMAC plus, 3K F9 and LightMAC plus constructions, and which are denoted as 2K sum ECBC, 2K PMAC plus, 2K F9 and 2K LightMAC plus respectively, and showed the similar level of security bound. So the summary is that all these constructions, namely the sum ECBC, PMAC plus, 3K F9 or LightMAC plus, they actually shared a similar design principle, namely applying a double block hash function followed by a sum function, and that sum function may take a single key or may take a pair of independent keys. But the important thing is that the hash key is independent to the block cipher key which is used in the sum function, and all of them have been proven secure up to 2n by 3 bits. But all the security, all these constructions have been proven secure under the assumption that they are proven in the standard model and in the single user setting. In Crypto 18, Laurent et al. Have shown an attack on DbHtS with a query complexity at least 2 power 3n by 4, and as a result of that, the proven security bound, which is 2 power 2n by 3, and the attack complexity 2 power 3n by 4, there's a gap. So the gap was finally kind of breached in the paper by Kim et al. In Eurocrypt 20, where the authors have improved the security bound of DbHtS from 2n by 3 bits to 3n by 4 bits, and as a result of that, the security bound of DbHtS constructions have been proven tight. However, as I mentioned earlier, that all these constructions and the generic design paradigm DbHtS, this is proven in the standard model and in the single user setting. So what will happen if you analyze the DbHtS construction in the multi-user setting? So first of all, let me explain that what is multi-user setting. So in the multi-user PRF game in the standard model, so adversary is not only given a single instance of the construction, but it actually is given u independent instances of the constructions. So namely, in the real world, adversary has access to u independent instance of the real constructions, namely CEK1, CEK2 up to CEKU. That means you can assume that u users are running so independent instances of the constructions, and in the ideal world, the adversary has access to u independent instances of random function. And finally, the adversary has to distinguish these two worlds. So this is in the standard model, that means where the adversary does not have access to the underlying primitive of the construction. But in the ideal cipher model, that means in the multi-user setting on the ideal cipher model, the adversary has access to the underlying primitive or the underlying block cipher if the construction is made up of the block cipher. And again, the PRF game in the multi-user setting and in the ideal cipher model is to tell you that what is the advantage of the algorithm A to distinguish the real world from the ideal one. Okay, so there's a trivial, generative reduction between the single user security and the multi-user security. That means if you have the single user advantage, for example, you analyze a construction, right, and you have a security bound of that construction in the single user setting, so you can trivially deduce the multi-user advantage of the same constructions as which is basically an upper bound by the number of users u times the single user advantage. For example, if you consider the DbHtS construction, then that we know that the single user PRF advantage of DbHtS is q to the power 4 by 3 by 2 power n, which was proven by Kim et al. In their Eurocrypt 20 paper. Then by this relation, the multi-user PRF advantage of DbHtS would be u times q to the power 4 by 3 by 2 power n. Well, so this bound is more or less good, but when the number of users reaches to the number of queries, that means when number of users is order of q, then the security bound would be q to the power 7 by 3 by 2 power n. Sorry for this typo. And that means this bound, this new bound is basically worse than the Burde bound. So as a result of that, the direct analysis of the DbHtS construction in the multi-user setting is basically a required thing than relying on the generic reduction. So in order to study the multi-user security of DbHtS construction, this was basically initiated by a work of Shen et al. In Crypto 22. So where Shen et al. Have analyzed the 2-key DbHtS construction in the multi-user setting under the ideal cipher model assumption, and authors have shown that the construction DbHtS is secure up to 2 power 2n by 3 many queries in the multi-user setting, and obviously the underlying assumption is that the block cipher is ideal cipher. And the authors have also instantiated the 2K DbHtS construction with 2K sum ECBC, 2K PMAC plus, 2K F9, 2K LightMAC plus, and showed similar security bound in the multi-user setting. However, recently some of their results have been pointed out to be flawed by Guo and Wang. So Guo and Wang first of all noticed that when the underlying double block hash function of the 2K DbHtS construction was instantiated using two independent polyhash function and two independent instances of the CBC function, then the claimed security bound was 2 power 2n by 3, but Guo and Wang have shown an attack on these two instantiation with the bound complexity. Basically, the flaw of their analysis cropped up because the authors of the Crypto 22 paper, that means the Shen et al., they have incorrectly argued that the probability of the cross collision event, namely sigma I equal to theta j and sigma j equal to theta I, is upper bounded by q square into epsilon square, where epsilon is the regular advantage of the underlying hash function. And they actually have assumed that these two events are independent, where in the practical setting they are not. Right? So, for example, if you consider these two independent instances of polyhash function, then sigma j equal to theta I is basically dependent on sigma I equal to theta j. So these two events are not at all independent. Similarly, for the case of CBC hash function. So on this observation, Shen et al. Have revised their paper based on the findings of this result by Guo and Wang, and they introduced a new event, which is basically a cover-free event, which the notion was introduced by DbHtS et al. In FAC 20. So the Shen et al. Proved 2n by 3-bit multi-user security of 2K DbHtS in ideal cipher model. However, the initial version of the paper contained a flawed analysis, which was pointed out by Guo and Wang, and that was later corrected by the authors. However, there are more to explore. There are more kind of flaws that remained in the paper. First of all, the security analysis of the instantiation in Shen et al.'s paper have not been done in the ideal cipher model. So that means they have analyzed the DbHtS construction in the ideal cipher model, but they did not consider the hash function can be instantiated with the block cipher. But when they instantiated the construction using this 2K sum ECBC or 2K F9, then the hash function was made up of the block cipher, and then they just simply plugged in the regular advantage or the universal advantage of the double block hash function using the standard result. So they have not analyzed the instantiation using the ideal cipher in the ideal cipher model. And moreover, the good transcript analysis for proving the security of double block hash then sum construction is incorrect, as they have used the sum of permutation result over 0 on power n, whereas according to their analysis, the analysis should have been used the sum of permutation result over a bijective function, that means over a restricted subset. So our result is that we have shown the multi-user security of 2K DbHtS construction and have proven it to be secure up to 2 power 3n by 4 many queries in the ideal cipher model. So the underlying assumption of our analysis is that the underlying double block hash function should be good. That means we call our double block hash function is good if the first hash function. So in fact, we have assumed that this hash function, double block hash function h, is basically a concatenation of two hash functions, two n-bit hash functions, h1 and h2. So we call a double block hash function to be good if each of the independent n-bit hash functions are universal and regular, and the probability of the cross collision between h1 and h2 is 0. Then we have instantiated the good double block hash function through two independent instances of polyhash function using the domain separation technique, and we have also proved the instantiated construction is achieving 3n by 4-bit security in the multi-user setup. So just a glimpse of the security proof. So we have proved the security of 2K DbHtS construction using the edge coefficient technique. So for that we need to identify some of the bad events, and we have to bound the probability of those bad events. So first of all, the bad events is that we have to avoid the alternating cycle of length 2 in sigma and theta. That means if there's a collision simultaneously in the sigma and theta value, then that has to be a bad event. Similarly, if there's a collision between the sigma values and the Ti values, or the theta values and the Ti values, then that will again be a bad event, because that will break the permutation incompatibility. well, we allow the individually sigma or theta can collide, but we do not want them to collide for too many queries. That means we will have to restrict the number of colliding pairs for sigma and theta. So namely, we have restricted the number of colliding pairs for sigma up to q power 2 by 3, and for the theta is again up to q power 2 by 3. So if the number of colliding pairs reaches the bound or is more than this bound q to the power 2 by 3, then we call it to be a bad event. We also have to restrict the event that there should not be an alternating path of length 4. So what do I mean by alternating path? So consider 4 queries I, j, k and l. Okay, so if there is a collision between the sigma values, so if there is a collision between the sigma values, which is denoted by these green edges, between the ith and jth query, and the theta j, I mean the theta value of the jth query collides with the theta value of the kth query, and the sigma value of the kth query collides with the sigma value of the lth query. Okay, so that will complete, or that will give you an alternating path, right? If you plug in the value, the sigma I theta I as a node of a graph, right? So this will basically create an alternating path of length 4. So we have to avoid this alternating path of length 4, and again this is a symmetrical event. That means if the theta value collides between ith and jth query, and the sigma value collides between the jth and kth query, and the theta value collides between the kth and lth query. And okay, so this is about the collision between the construction queries, but we also have to we also have to identify the collision between the construction query and the ideal cipher query. Namely, if there is a collision between the key and input in the ideal cipher queries, namely if ki equal to jj, where jj is basically the ideal cipher key, and the sigma ia, that means for the ith query of the ith user, that collides with the ideal primitive query, right? Similarly, if there is a collision between the key and input in the construction queries, namely if for the two users, ith and jth user, their key collides and their sigma value also collides. Similarly, for two users, if their key collides and their theta value also collides. And finally, we also do not want the block cipher key and the hash key of the construction simultaneously collides for two users, right? So for the ith user and the jth user, if their block cipher key collides and their hash key collides, then we call it to be a bad event. By analyzing all these bad events, we have obtained this bound, which is roughly of the order of q to the power 4 by 3 by 2 power n, by assuming this universal advantage and the regular advantage of the underlying hash function epsilon to be 2 power n. And finally, if the bad events do not happen, that means for a good transcript, we have analyzed the good transcript by applying the mirror theory result over a bipartite graph, which was a result proposed by Kim et al. In Eurocrypt 20 to derive the desired 3n by 4-bit bound. So to finally wrap up the discussion, so we have improved the multi-user security bound of double block hash sum construction from 2n by 3 bits to 3n by 4 bits, and due to the result of Laurent et al. In Crypto 2018, our proven bound is tight. Well, our result does not address the block cipher based double block hash functions. That's why we have instantiated the underlying hash function using polyhash function, which is an algebraic hash function. And as a result of that, our result cannot be applied for proving the 3n by 4-bit multi-user security of block cipher based DbHtS constructions, namely for the 2k PMAC plus or 2k Lite Mac plus. So for that, we need a dedicated analysis. So to prove the security of such DbHtS construction, one needs to derive the regular and universal advantage of underlying block cipher based double block hash function in the ideal cipher model, which we believe is a challenging open problem. So that's all. Thank you.